So here's the easier method that you're going to use from now on, and I'm sure you'll be happy to see that. Previously, what we did, we used our X bar, right? We used our X bar as the test statistic, which was equal to 170, which was 178, correct? And to do that, we wanted to compare that to the X bar L, which is the critical point or the cutoff point. But instead of that, I'm going to use a standardized test statistic, which you know what is it, right? So from that X bar, of course, we're going to use the X bar because this is our evidence. But I'm going to convert that into a standardized test statistic. Why this? Because my cutoff point is not going to be in terms of X bar L anymore. So I'm not going to use that. But instead, I'm going to use a cutoff point or a critical point in terms of Z, right? So when alpha is given to be 5%, I know from the Z table that a Z value such that this area is 5%. Okay, I know that. I can read it easily. It's 1.645, right? How did we find that? We looked in the Z table in an area here equal to 95%, which is the complement of the 5%. So this is my critical value that I'm going to compare any Z value or any test statistic for it. And in other words, the 1.645, okay, is the value, here we go, that now determines my rejection region. So if I find any Z test statistic to be inside, that means greater than 1.645, then I will reject, otherwise I will not reject. So in our example, we found Z to be 2.4, or we will find Z to be 2.46. We did not find it before, now we are finding it. So we collected the sample, we found the sample mean to be 178. We are assuming that mu is 170 if HO is true. So we find the Z statistic to be 2.46. 2.46, where it is located, 2.46 is here. Okay, it's greater than 1.645. It's inside the rejection region, right? So we reject HO. And we reject HO in favor, of course, of the alternative hypothesis, which is H1. All right. And here we go. This is exactly the same conclusion that we ended up with in using the X bar L. But this is a good news for you. You're not going to do all that exercise of finding the X bar L. If you are then told, all right, then in real life, what would be that large value, then you can find it. You can find it from 1.645, and this is something that you learned how to do in previous topics. All right. So the rejection region, I hope that you have understood it. However, unfortunately, it has a drawback. Okay, it has a weakness. What's that weakness? The problem with the rejection region is that it simply tells me whether to reject or do not reject. So it's either a yes or a no response. Okay, so what's happening here is that I cannot really give a strength of my evidence. Was my evidence strong? I don't know. All what I know is that I was in the rejection region. How strong it is, I cannot tell. Okay, let me give you a very quick illustration of it. Okay, let's say, I'm sorry about what's happening, but here we go. This is all our rejection region. So if we find from the sample that we are here, we reject. And if we are there, we reject. And if we are also here, we are rejecting. But we know that the probability of finding this value or that value or that value is not the same. Here, it's very unlikely to see that, okay, which is very, very strong evidence. And you see these three values give us the same conclusion that we reject, but we cannot quantify that. Now, in managerial decisions, we have so many other factors, not only the statistical factors that we are using here. So what we have to do, usually managers, what they do, they give weight for every factor, and based on that, they may define the decision. Unfortunately, using the rejection region, they are not able to give that weight. So we need a weight for that. How to do this? We can use what we call the p-value. It gives a weight for the evidence. What's that p-value? Look, this is very, very important description or definition for the p-value. P-value is the probability of observing a test statistic, which is X bar in our case, or Z if you are using the standardized, at least as extreme as the one computed, given that the null hypothesis is true, right? So in the previous example, when we found X bar to be 178, the question is, how likely it is to see an X bar equal 178 in a sampling distribution that has a mu, because HO is supposed to be true, equal to 170. Okay, so here we go. It's here. We found 178, which is somewhere here. The question was how likely it is that we'll see 178 in a sampling distribution that has a mean equal to 170. That would be the p-value. Okay, so the question, the p-value in this case will be what the probability that x is greater than that 178. This is a p-value. It gives us a very, very good quantitative measure for our evidence. All right, so let's find the p-value that we have in the previous example. So as we said before, from the definition of p-value, what the probability of observing a sample mean as least as extreme as our X bar to be 178. Given, this is very important, that the null hypothesis is true. Now, look here in this calculation that I'm going to show you, it will be a very, very good illustration that why the null hypothesis is very important for our procedure. Otherwise, you cannot proceed. Look at this. In fact, we did it before, but here it will be much emphasized. It will be clear for you. So the p-value, it's the probability to find an X bar greater than the value that we have found, right? Because that was consistent with our alternative hypothesis. So as we did before, we will be standardizing. So subtracting mu divided by standard deviation. Here we go. So it's equal to probability that Z is greater than 2.46. And you see, I could not have come out with that if I don't have a mu. And I would not have a mu if I don't have my null hypothesis to be assumed true for now. So the question is, what's the probability that Z will be greater than 2.46? I look in the Z table, but as you know, the Z table gives us probability from the lower tail to any specific value, but that's okay for us. So P of Z greater than a value is 1 minus P of Z less than that value. So we'll get 0.0069. It's a very small value, right? So the probability that we will observe a sample mean to have a value of 178 drawn from a population that has a mean of 170 is 0.69%. Such a small probability. Okay, so we are saying that it is most probably it's very unlikely event, all right, to see that. And this will allow us then to reject the null hypothesis in favor of H1, right? All right, so when you learn really how to find the p-value, you have a very powerful tool in your hands. But there is one more question that comes to your mind. how small the p-value should be in order to be considered as a very strong evidence for your alternative hypothesis. In fact, there is no clear answer for that. Depends on the effects of type 1 error and type 2 error that you will have, right? So it's not very easy to answer this question, but this is something also that you don't have to worry about it, given the nature of the introductory nature of our course here. However, there are some guidelines about the p-value that are widely used in the research environment. Okay, so when we say p-value is less than 1%, we say that we have an overwhelming evidence. While if p is between 1% and 5%, then we say that we have a strong evidence to support the alternative hypothesis. Then if p-value is I was referring to these. Okay, then what about if p-value is between 5 and 10%? We say that it is an evidence, but it's a weak evidence. And if p-value exceeds 10%, then we say that there's no evidence. That's it. There's no question about that. Okay, so these are just guidelines. Again, depends. It's a case-by-case basis, but for you, for this course, the criterion will be given to you. All right. So for us, as we really don't know the background of the problems that we'll be using to practice our now knowledge about the hypothesis testing, what we're going to do is that we're going to use alpha as our criterion. So in fact, the p-value approach can be used in a similar method that we have used the rejection region method, right? In the rejection region, what did we do? We have that very, very, very ugly, curve, but bear with me, it's okay. Let's say that was our rejection region, and we rejected when the z value was somewhere here, and that was our z critical, right? Now, remember, what's that area? This is alpha. So what we're going to do is this. If our p-value is less than that alpha, we're going to be also rejecting. You see, it's like we are inside. So less than alpha, that means, for example, here, this is less than alpha. If alpha is 5%, this can be the 2% out of the 5%. So here we go. If the p-value is less than alpha, we will be rejecting the null hypothesis. All right, so it's like we are here. If, on the other hand, p-value is greater than alpha, then we will not reject the null hypothesis. So this is the criterion that we're going to use if we are using the p-value and we need to make a conclusion about our test. All right, so to just wrap up the concepts and our conclusions from the test, here we go. If we reject the null hypothesis, what we are saying that there is enough evidence, okay? So there is enough evidence to support the alternative hypothesis. And if we do not reject the null hypothesis, we say that there is not enough evidence, okay, statistical evidence to be precise, okay, to support our alternative hypothesis. All right, this is very, very important. Remember that the alternative hypothesis, not the null hypothesis, is the focus of our conclusion. All right. Of course, the test procedure is not possible without the hypothesis test, without the null hypothesis assumed to be true. But everything is about the alternative hypothesis. It's about, this is what we are investigating. Okay. The alternative hypothesis, and that's why it's called the research hypothesis. Please remember this definition for the alternative hypothesis. It's called the research hypothesis.